This is section 4.3, beginning curve sketching. 4.5 is also a section on curve sketching. A lot of important topics here. Okay, 4.3, how derivatives affect the shape of a graph, page 293. Remember, slope or derivative means slope. Okay, so if you look at the picture here, the slope keeps changing. Positive slope, negative slope, positive slope. Positive slope, the function's increasing. Negative slope, function's decreasing, back to increasing. Okay, so if f prime of x is greater than 0, that means m is positive, then f is increasing on the interval. If f prime of x is less than 0 on an interval, then f is decreasing on an interval. Okay, think of positive slope, negative slope. Okay. All right, we have the first derivative test. It's on page 294. Let's take a look at these examples here. Local maximum, local minimum, neither maximum nor minimum, neither maximum nor minimum. Okay, so in each case, the derivative is 0, slope is 0. What's at a local maximum? Well, it goes from increasing to decreasing. Okay, f prime greater than 0, f prime less than 0. Local minimum, it goes from decreasing to increasing. F prime less than 0, f prime greater than 0. Here, you have neither a maximum or min because a little bit to the left of the graph, the function's increasing, and a little bit to the right, the function's also increasing. And over here, you have neither a maximum nor a minimum because the function is decreasing, slope is 0, and then it continues decreasing. All right? So, first derivative test. If f prime changes from positive to negative at c, then f has a local maximum at c, at a critical point. Okay, increasing, decreasing. If f prime changes from negative to positive, negative, positive, then f has a local minimum. Okay. If f prime is positive to the left and right of c, like this, or negative to the left and right of c, then f has neither a local maximum nor a local minimum at c. So this is how you can tell if you have a maximum or a minimum. Okay, look at the picture. Maximum, increasing, decreasing. Minimum, decreasing, increasing. In these two cases, you don't have a maximum or minimum because it might go increasing, increasing, or decreasing, decreasing. Okay, so first derivative equal to 0 does not guarantee you have a maximum or minimum. All right. Okay, on page 296, we have the concept of concavity. Okay, concave upward or concave up, and concave downward or concave down. I will abbreviate CU and CD, concave up, concave down. Concave up, think of it as U shape, like the letter U. If you think of the letter U, very helpful that U shape starts with the letter U. If the graph is curving as a U would, it's called concave up. If it's curving like an upside down U, that would be concave down. So something like this. Now you don't have to see the entire U. If you just see a part of it, like so, that's still considered U shape. That's concave up. This is concave down. Okay, so if you look at this picture, concave down, upside down U shape. Concave up, U shape. Concave down, upside down U shape. Concave up, concave up, concave down. So U shape or upside down U shape. Okay. Now, the second derivative is what controls concavity. It's the rate of change of the slope. So if you look at this situation, the slopes are increasing. It's getting steeper and steeper. Here, the slopes are decreasing, smaller and smaller. Okay? It's like saying f prime is increasing, f prime is decreasing, or rate of change of f prime, which is f double prime, positive or negative. Okay, so here's our concavity test. F double prime greater than 0 means concave up. F double prime, second derivative, less than 0 means concave down. Second derivative positive, U shape, concave up. Second derivative negative, concave down. Okay. On page 297, you have an inflection point. An inflection point, function's continuous and the curve changes from concave up to concave down or from concave down to concave up. Okay, inflection point. So this is an inflection point. It switches from either concave up to concave down or vice versa. Here's an inflection point. Changes from CU to CD. Okay. So figure 9, here's an inflection point. Here's an inflection point. Concave up, concave down, concave up. Okay. This graph has no inflection point. Looks like it's always concave up. Now we have a second derivative test for maximum and minimum. Let's go back and look at the maximum and minimum case. Here's a maximum, derivative of 0. What seems to be the concavity? Concave down. Here's a minimum, what seems to be the concavity? Concave up, which means second derivative positive, second derivative negative. So second derivative test for max and min, if f prime of c equals 0, critical point, and f double prime of c is greater than 0, concave up, then f has a local minimum at c. The picture is going to be something like this. If f prime equals 0, slope is 0, and f double prime less than 0, concave down, then f has a local maximum at c. You can put this on your cheat sheet also. So you can put this if you want, and U shape, upside down U shape. Okay. All right. Okay, so let's get started. Page 300. We have to go up to problem 53. So here we are. 9 to 21. Okay, 25 to 30. 25, 31, hopefully you can read that. And what, 37 to 53, more curve sketching. So find intervals of increase and decrease, local max and min, intervals of concavity, inflection points, all that good stuff. 49, you can see the directions there. And we have to go up to 53, which I think you can see there. Okay. We'll start with 1 and 2. All right, so I will just say the answers. Unfortunately, I'm not able to write it since I'm holding up the book. Okay, so 1 and 2, I'll do 2 since it's even. You don't have the answer in the back of the book. The open intervals in which f is increasing. Okay, so it's increasing. All of these should be with parentheses. 0, 1, union here to here. So what's that? Parentheses 3, 5, union 5, 7, I think. 1, 2, 3, 4, 5, 6, 7. All right, so 0, 1, union 3, 5, union 5, 7. How come I can't just say 3 to 7? Right here, strictly speaking, you're not increasing. The slope is 0 just for a split second, and then you increase again. B, open intervals where f is decreasing, where you're only going down from here to here. So that would be from 1 to 3, parentheses 1, 3. Okay. C, concave up, U shape. So maybe from here to here. So that would be what? 2, 4, all with parentheses, union 5, 7, U shape. So everything else is concave down, upside down U shape. From 0 to 2, union here to here. So where's here? 2, 3, union 4 to 5. And then the coordinates are the points of inflection. Point of inflection, the graph changes concavity. So that's right here. So that's what? 2, 2. And here, so where's here? 1, 2, 3, 4, 4, 3. And one more here, which looks like 5, 4. 2, 3, 4, 5, 5, 4. Yeah. Okay, 9 through 21. Do all this analysis. Okay, so I'll show you some of these. Typical way to work these out is to find the first and second derivatives, set them equal to 0, and then do a lot of stuff after that. So here we go. Number 9, here's the function. Take the first derivative, 3x squared minus 6x minus 9. And if you can factor. So factor out the 3 and factor further 3 times x plus 1, x minus 3. Second derivative, 6x minus 6. Okay, set the first derivative equal to 0. -1 and 3. Find the y coordinates. So the function values, plug in -1 here and here. Okay. And let's see. Plug in -1 here and here and here. So it's -1 minus 3 plus 9 plus 4. That comes out to be 9. Plug in 3, 27 minus 27 minus 27 plus 4 is -23. So -1, 9, and 3, -23. Okay, those are called critical points. Slope is 0. It might be a maximum or a minimum. Then I have to do a sine chart. Okay, so the derivative was 3 times x plus 1, x minus 3. Plug in, I plunked down -1 and 3, pick something here, here, and here. So -2, 0, and 4. Okay, plug in to see the sign, positive or negative. You plug in -2. This plus represents the 3. That's always positive. Okay, -2 plus 1, negative. -2 minus 3, negative. So I have a positive times a negative times a negative. That's a positive. Okay, 0. 0 plus 1, positive. 0 minus 3, negative. So a positive times a negative is a negative. Okay, then I plug in 4. Looks like everything is positive. 3 is positive. 4 plus 1 is positive. 4 minus 3 is positive. The product is positive. Positive. Okay, so positive first derivative increasing. Negative first derivative decreasing. So it asks for intervals of increase and decrease. F is increasing from -infinity to -1, union 3 to infinity. -infinity, -1, union 3 to infinity. And F is decreasing only between -1 and 3. Okay, my abbreviation for increasing is arrow up, going this direction, arrow down for decreasing. Okay. If the graph goes from increasing to decreasing, relative maximum or local maximum. The graph goes from decreasing to increasing, minimum. Okay, so I have this. -1, 9 is a relative max or local max. 3, -23 is a relative min. You do the same thing for double prime. Set f double prime equal to 0. 6x minus 6 equals 0. That's easy. X equals 1. Plug in 1 to the original. 1 minus 3 minus 9 plus 4 comes out to be -7. So 1 comma -7. Do my sine chart for f double prime, 6x minus 6. Plug in 0, 6 times 0 minus 6, negative. Plug in 2, 6 times 2 minus 6, positive. Concave down, negative second derivative. Concave up, positive second derivative. Okay, so intervals of concavity, f is CD, concave down from -infinity to 1. Okay. Concave up, U shape from 1 to infinity. I do have a change in concavity, so 1, -7 is an inflection point. And here's the graph. Maximum at -1, 9, minimum 3, -23, inflection point at 1, -7, increasing, decreasing, increasing, increasing up to -1, decreasing to -3, increasing, concave down, upside down U shape until I reach 1, and then U shape the rest of the time. Okay, so here's a typical curve sketch type of problem that we have in this section. Okay. Okay, jumping ahead to problem 37, we'll do several of this type. X cubed minus 12x plus 2. Okay, take two derivatives. F prime is 3x squared minus 12, which is 3 times x squared minus 4, or 3 times x plus 2x minus 2. F double prime, 6x. Set f prime equal to 0. Set this equal to 0 plus or minus 2. Plug in 2. 8 minus 24 plus 2, -14. Plug in -2. -8 plus 24 plus 2, 18. So 2 comma -14, -2 comma 18, those are my critical points. Now we do a sine chart. Plunk down -2, 2, pick something here, here, and here. So something here is like -3, 0, 3, do a sign analysis. 3 is already positive, so that's positive, positive, positive. -3 minus 2, negative. -3 plus 2, negative. -3 minus 2, negative. Positive times negative, positive. 0, 0 plus 2, positive. 0 minus 2, negative. Positive times negative, negative. 3, 3 is positive. 3 plus 2, positive. 3 minus 2 is positive. They're all positive. The product is positive. Okay. Positive first derivative, increasing, increasing, decreasing. So f is increasing from -infinity to -2, union 2 to infinity. F is decreasing just between -2 and 2. If the graph goes up, then down, relative maximum, -2, 18. Graph decreases, then increases, relative minimum at 2, -14. Set y double prime equal to 0. 6x equals 0. No, that means x equals 0. Very easy sine chart. You plug in a negative, plug it in, you get a negative, plug in a positive, positive. So function is concave down from -infinity to 0. Concave up from 0 to infinity. So 0, 2 is an inflection point. 0, 2, I plugged in 0 back to the original. Okay. So here's my graph. Increasing, decreasing, increasing, maximum, minimum, inflection point. Okay, 13 is definitely harder because it's trig, but they only want the closed interval from 0 to 2 pi. Well, that makes sense. This is a periodic function. So once you have 0 to 2 pi, you got the whole thing. Then you can just copy and paste both to the left and to the right. Okay, plug in 0, I get 1. Sine of 0 is 0 plus cosine of 0 is 1. And since we know it's periodic, 2 pi also gives me 1. Okay, f prime, first derivative is cosine x minus sine x. Double prime is negative sine x minus cosine x. Set f prime equal to 0. Cosine x minus sine x is 0. Move over to sine x. Cosine x equals sine x. Divide both sides by cosine x. Tan x is 1. That's at pi over 4 and 5 pi over 4. Okay, plug in pi over 4 to the original. You have root 2 over 2 plus root 2 over 2, which is root 2. 5 pi over 4, you get negative radical 2 over 2 minus radical 2 over 2. That's equal to negative radical 2. It's about 1.4 and negative 1.4. Okay, then I do a sine chart for this. So I plug in 0. Cosine of 0 is 1. Sine of 0 is 0, positive. Between pi over 4 and 5 pi over 4, I plug in pi. Cosine of pi is -1. Sine of pi is 0. That's -1, so negative. And then after 5 pi, or how about 2 pi? Well, 2 pi, you already know it's the same answer as if I plug in 0. So it's also going to be 1, positive. So increasing, decreasing, increasing. So f is increasing from 0 to pi over 4. Union 5 pi over 4 to 2 pi. F is decreasing from pi over 4 to 5 pi over 4. All right, second derivative analysis. Set f double prime equal to 0. So move over to cosine, divide by cosine. I get tan x is -1. That's going to be 3 pi over 4 and 7 pi over 4. This is negative radical 2 over 2, radical 2 over 2. This is the same thing except positive for x and negative for y. So f of 3 pi over 4, f of 3 pi over 4 is radical 2 over 2 minus radical 2 over 2, 0. F of 7 pi over 4, that's negative radical 2 over 2, positive radical 2 over 2, that's also 0. I'm going to do my sine chart. Okay, plug in 0. Negative sine 0 minus cosine 0, it's -1, negative. Plug in pi, negative sine of pi, 0, minus cosine of pi, that's -1 or 1, positive. And you already know the answer is the same when you plug in 2 pi or pi, so -1 also. So concave down, concave up, concave down. So these are inflection points. Change in concavity. So F is CD. from 0 to 3 pi over 4, union 7 pi over 4, 2 pi. Function is concave up from 3 pi over 4 to 7 pi over 4. Here's the graph. Increasing to pi over 4, you have a maximum. Decreasing to 5 pi over 4, minimum. And then increasing. Starts off at concave down until the inflection point, then concave up to the inflection point, then concave down. So that's the way that one works. Okay, then some of these other graphing type problems. (25) A and B. F prime greater than 0, increasing, F double prime less than 0, concave down. So increasing, but upside down U shape. B, F prime less than 0, decreasing, F double prime greater than 0, concave up. So decreasing, concave up. Okay, and while I'm at it, let's do 24. I know it's an even problem. Okay, F prime less than 0, F double prime less than 0. So decreasing, concave down, decreasing, concave down, decreasing, upside down U shape. And B, F prime greater than 0, increasing, double prime greater than 0, concave up. So increasing, concave up U shape, like that. So there we go. Okay, 27. F prime of 0, 2, and 4 is 0. You have a horizontal tangent at 0, 2, and 4. Horizontal tangent, slope is 0. This says the function's increasing from negative infinity to 0, union 2 to 4. That's what F prime greater than 0 means. Increasing. Decreasing F prime less than 0, between 0 and 2, and 4 to infinity. Concave up from 1 to 3, and concave down the rest of the time. Okay, so here we go. Slope is 0, slope is 0, slope is 0. Increasing to 0, then decreasing, then increasing, then decreasing. Concave up only between 1 and 3, the rest of the time here and here, concave down. So there's my graph. Problem 29. F prime of 5 is 0. Slope is 0. F prime of x is less than 0 when x is less than 5. So decreasing until I reach the 5. And then increasing after that. F prime greater than 0 when x is greater than 0. Okay, increases. F double prime of 2 is 0. Concave up. Oh, I'm sorry. F double prime of 2 is 0. F double prime of 8 is 0. Right. So these might be inflection points, and they are. Double prime less than 0. Concave down for x less than 2 or greater than 8. Concave down. Concave up, second derivative greater than 0 between 2 and 8. U shape. And limit as x approaches infinity or negative infinity of the function is 3. So I go way out to the right and to the left, we approach y equals 3. So here's the graph. Decreases, inflection point, concave up, minimum, increasing, inflection point, switch to concave down, and increasing. Okay. There's a lot that's involved in a lot of these problems here. Okay, 4.351. Radical x squared plus 1 minus x. So the derivative is 1/2 x squared plus 1 to negative 1/2 times the derivative of the inside 2x minus 1. That's x over radical x squared plus 1 minus 1. Then I do the second derivative. It's a little bit messy. Bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 1/2 x squared plus 1 to negative 1/2 times 2x, all over the square of the denominator, x squared plus 1. And the derivative of negative 1 is 0. Okay, touch up. I canceled that 2 here. I have x times x squared over radical x squared plus 1. This actually comes out very nice if I multiply top and bottom by radical x squared plus 1. This becomes x squared plus 1. These will cancel out, so I have a minus x squared. These two combine to be x squared plus 1 to the 3/2 power. X squared plus 1 to the 1, x squared plus 1 to the half, so x squared plus 1 to the 3/2. And notice the x squared cancels out. So I have 1 over x squared plus 1 to the 3/2. And I notice no matter what I plug in, this is positive. So F is automatically concave up everywhere, and it's concave down nowhere because it never changes concavity. So automatically I have no inflection point. Let's try to set F prime equal to 0. So this thing equal to 0, move over to 1, multiply both sides by radical x squared plus 1, square both sides, x squared equals x squared plus 1. That is impossible. That's a contradiction, right? If you try to solve by subtracting x squared, you'll get 0 equals 1. So this expression can never equal 0, which means the whole number line is of the same sign. There's never a change in increasing or decreasing. So plug in anything you want. Easiest number is 0. I get 0 minus 1 negative. So the function's decreasing everywhere, increasing nowhere, no maximum. When x goes to infinity, y actually approaches 0. When x approaches negative infinity, y approaches infinity. Okay, let me actually show you that. Okay, if I plug in a super big negative, it's pretty clear. This would be a double negative, positive, and this is a big positive. So big positive plus big positive is positive. What's less obvious is what happens when x approaches positive infinity. The trick is to multiply top and bottom by the conjugate of this. So that gives me x squared plus 1 minus x squared over x squared plus 1 plus x. And the numerator comes out to be 1. And now when x gets big, the ratio approaches 0. Okay, so we do approach 0. The graph looks something like this. It's always positive, always decreasing, concave up, passes through 0, 1. Okay, so that's kind of interesting. And let's see, just one more of that type I wanted to show you. 43. F of x equals x square root of 6 minus x. So a little bit more clumsy. X times 6 minus x to the half. So the domain, 6 minus x, the thing underneath the square root has to be greater than or equal to 0. Add x to both sides. 6 is greater than or equal to x, or x is less than or equal to 6. So I cannot plug in 6.1. The domain is negative infinity to 6 bracket. Intercepts. How do I get 0? Well, 0 and 6. So 0, 0, 6, 0. There's no symmetry. You can tell there's no symmetry just from the domain, right? You have a domain like that, you're not going to have symmetry. There are no asymptotes, looks like. When x approaches negative infinity, y approaches negative infinity. So negative 1,000,000, that's negative big, positive big. So the product is a negative big number. And I don't have to say what happens when x goes to positive infinity. I'm not even allowed to do that. I can't go past 6. So no need to worry about that. Okay, now for the derivative test, a little bit clumsy. There's a product. So product group. First times derivative second, x times 1/2 6 minus x to negative 1/2 times negative 1, plus the second times derivative first, but the derivative of x is just 1. So I have that. Okay, clean it up. This is negative x over 2 radical 6 minus x plus radical 6 minus x. Get a common denominator, multiply top and bottom by 2 radical 6 minus x. So negative x plus 2 parentheses, that times that, very conveniently, is 6 minus x. Clean up some more. This comes out to be 12 minus 3x. That's my first derivative. Double prime is really messy. Bottom times derivative of the top, -3. Plus the top times derivative of the bottom. Let's see, I have 2 times 1/2, 1, 6 minus x to -1/2 times -1. Okay, so let's see, this is going to come out to be -6 radical 6 minus x plus 12 minus 3x over radical 6 minus x over 4 times 6 minus x. All right, I decided to multiply top and bottom by radical 6 minus x to clean it up. So that becomes -6 times 6 minus x. This becomes 12 minus 3x. This becomes 4 times 6 minus x to the 3/2 power. Touch up 3x minus 24 over 4 times 6 minus x to the 3/2. Okay, set f prime equal to 0. Here's the first derivative. When is a fraction equal to 0? When the top is 0. So that's going to be x equals 4. So plug in 4 here and here. 4 comma 4 radical 2. Okay, y prime comes out to be this. Plug in something smaller like 0, positive. Plug in something like 5, positive, but this is negative, so negative. So the function's increasing from -infinity to 4, decreasing from 4 to 6. 4 comma 4 radical 2 is an absolute max as well as a relative max. Okay, how do I know? The graph, all it does is go up, it goes down, so that's all. And you can do your intervals of increase and decrease if you wish. Okay, set f double prime equal to 0. Make the numerator 0, x equals 8, but x equals 8 is not in my domain. It's not under consideration, so forget about it. So the whole graph is of the same concavity. I just have to plug in anything, like 0. I get a negative quantity. So the graph is always concave down. All right, so f is CD from -infinity to 6, concave up nowhere, and there's no inflection point. So here's all the graph does. Goes through the origin, 6, 0, maximum, always upside down U shape, increasing, decreasing. So there we go. That's the way that works. All right, so this is section 4.3 on curve sketching for Calc 1.